Tonight is May the 23rd, 2020. I've got another little amplifier here for you tonight that I think has a couple of interesting points about it. I don't have the tubes plugged in yet because that's kind of part of the unique part of this video, and I'll show you here in just a minute. But first, I think I want to show you something I've been meaning to do for quite some time, and that is just actually gathering some data. Okay, well, first of all, the reason I built this is I got this transformer here some time ago. It's a Chicago standard. It's called a BO-13. It's one of their very highest quality audio transformers. These size transformers here, these 20-watt size transformers made by James, by UTC, and by Acrosound, and even the Triad ones, all measure 20 henries on the primary side. This one measures 40 henries. So I figured it probably would do very, very well at low frequencies because it has more inductance. It probably won't do, as I suspected. Of course, I've already tested it, so I already know the answers to this. I'm not trying to act like I don't. And I figured it wouldn't do quite as well at the high end because of all of the shunt capacitance in it. But I'll show you how it performs. But I thought I would do something that's really kind of important. It's even important to me, and maybe I can remember it without having to watch my own video. And that is, have you ever wondered just how to deal with your power supplies? And you say, well, can I use this transformer? Should I use it in a full wave center tap? Should I use it in a voltage doubler? Should I use it in a bridge? How in the world should I use this? Should I use a choke input filter or a capacitor input filter for like a pi network? And these things we're always scratching our head over and go, well, what's going to be the final voltage? Well, here's the answer. Here's the answer. You got to make some measurements. I don't know if you can see this or not. I want to scope in there so that you actually can see it. This transformer right here, quite a nice little transformer. I believe you can read that. Anyway, it's got 115 volt primary, 5 volt 3 amp, 6 volt 8 amp. We don't really care so much about that. 700 volt, 200 milliamp DC. 200 milliamps DC. Now that's a different kind of rating. I don't want to digress too many ways here, but I suggest you go and to the let me back out here. I'm going to back in and out a couple of times here. That you go to the website here for Hammond Transformers and get some of their information. And a lot of your power supplies are rated. You will see a rating here on the secondary for DC. But if it has an AC rating, then you can let me see if I can find it here. Yes, here it is right here. Sorry, I got to back out again because this is really important to see. If you use a FWCT, full wave center tap, if your secondary rating of your transformer is an AC rating, then your current DC is 1.54 times the secondary current AC. So it's 1.5 times. Forget about the 0.54, just say 1.5. So if you had for example, if you had a 200 milliamp AC rating, IAC, you got VAC, volt AC, IAC, current AC. If your IDC is 1.54 times the secondary IAC, that's important to know. Assuming that you have an AC rating on your transformer. Now, a lot of transformers don't have the AC rating. They already have the DC rating. I hope you can read that. It says 200 milliamps DC. So you'd have to actually divide that by 1.54 to get its AC rating, which is not exactly important. Well, it is important. It's not especially important to what I want to show you, but that is one important thing to know about a transformer. And there's always a lot of things to know about transformers, and we're always scratching our heads over them and trying to get them exactly straight. But here is, while that being important, here's another thing that's of real importance. And it's a mistake that we all make. I make it all the time. And that is, I look at this thing and I say, well, it's 700 volts. So it's 350 volts each side, right? Well, is it? And this is, and is that its open circuit voltage, or is that its loaded circuit voltage? Is that its loaded voltage at 200 milliamps DC? You know, after it runs through the power supply and everything? Well, you don't really know. You know this is kind of close, but you don't. You know, the difference between what you think you're going to get and what you get could be 50, 75, even maybe 100 volts. It can be a lot different than what you think. So what we're going to do is measure it. We're going to measure its unloaded voltage right now. I'm going to flip this thing over and hook up a digital meter to it and plug it in with no tubes in. So we're just running it, running the transformer open circuit, and we're going to see what it is. We're going to measure the input voltage, and we're going to measure the secondary voltage, and we're going to write it down. So let me flip this thing over. Okay, to start with, remember that transformer was 115 volt input and 700 volt output, but look what my input voltage is. It's 121.31 volts. This is accurate. So let's call it 121 volts. So we got a transformer. I'm going to show you all this in a minute. 121 volts AC. I'm just drawing it out here. Now, very, very carefully, I'm going to turn it on. Well, no, I'm not going to turn it on yet. I'm going to go from ground to one side right here of the AC. Okay. Now this is bogus because it's just such a sensitive to me. Now let's turn it on here. Remember we said that half of it, you know, according to the little diagram, half of it would be 350. Well, it's actually 393 point something. It's going to vary a little as line voltage varies. 392 each side. 392 and 392. Well, that's higher than 700, isn't it? That's more like 800. Okay, now the next step is, what is the DC voltage going to be? Now I've got to plug it together and let it warm up, and then we're going to measure the DC voltage, and then we're going to do a little bit of math, and we're going to go, and we're going to learn something here. Okay, all the tubes are plugged in. It does not have a driving signal, but look what the voltage is now. Remember, it was supposed to be 700 volts. It's really 380. Didn't drop much. 380 each side. It was 392 unloaded. Fully loaded, it's still 380 with 100 milliamp load. It's got all the tubes in it. The voltage is the same on the input. No use in continuing to measure the same thing, because I've actually got a monitor up on the wall that's measuring this too. Okay, now let's see what the DC voltage is on the plate. Okay, disconnect this one with one hand. Always working with one hand. We don't want to get clobbered here. And let's look at the plate voltage on pin 3. Let's just go at, well, we don't have to go there. Let's go, let's look at the plate voltage on the output side of the choke. And that's right there. .432 volts. 432 volts DC. 432 DC. Okay. This is an experiment in DC. So our 380 each side is turned to 380 AC is turned to 432 DC. Now what is that ratio? That's 432. Look here. 432 divided by 380. Can you see that? 1.1368. 113%. That's real. 113%. Let's see. Let's see. Yeah, that's on the output side of the, actually right off of the capacitor, it's 447. Can you see that? That's right off of the rectifier pin, 447. So that's going to be on your first capacitor. So that's actually an important number too. 447. 447 enter 380 divide 1.17. About the same though. So it's about 117%. I always guessed it about 120. 117.6. Call that 118%. So what is this telling you? It's telling you that when you get a transformer and you're not sure, what you do very carefully so you don't electrocute yourself is you plug it in and you measure its open circuit voltage. Well, and then can we get some common sense between the open circuit voltage and the loaded voltage? Well, of course we can. 380 divided by 392. 392 divide. That's about 97%. 96.94. 97%. The lighting is just terrible in here, huh? I know it is. But it's really important that you see those numbers. So it's about 97%. You take your open circuit voltage and you take about 97% of that, and then you take that voltage, which we're going to end up with 380. We're going to take the 392.97 times, there's our 380 right there. Let's see, F fixed 2 gets rid of the decimal place at 380 volts, and then we're going to multiply that times 1.18, 118%. There's our 448 volts. Now, is that going to work perfect for every transformer every time? And the answer is going to be no, but it's going to be darn close. It's certainly a good place to start. And the reason I say it's not going to be perfect every time is because if I had been using say a 500 milliamp power transformer in here, it wouldn't load down as much. So it would probably be just a little bit higher. Now if this was a 150 milliamp transformer, 150 milliamp output, you know, DC loaded, then it might be a little bit lower. But this is this may not be a total bullseye, but I tell you, it's going to hit within the first ring of the bullseye. There you go. To me, that's really important. And now that I've made a video of it and made all these measurements correctly, maybe I'll even remember it. I still guess about 120%. But you really ought to know. Well, if you actually go to the DC, the 445, let's use that one. The 445 from the 392, from the open circuit to the DC, what would that be? That would be 432, let's just go directly there, divided by 392, that's 110%, 1.1. So in other words, if you want to take the shortest shortcuts, you could measure your open circuit voltage. This is half the transformer because you got this into like a 5U4, 2 diodes, center tap is grounded, full wave center tap. Not a bridge, not a voltage doubler, any of that kind of stuff. Full wave center tap. Your DC output voltage under load, at a reasonable load, in this case it's 50% loaded, it's going to be about 110% of this right here, of your unloaded transformer voltage. Assuming, like I say, that your transformer is not really small and you're loading it heavily, or really large and you're just barely loading it. If it's really small and you're loading it heavily, it's probably going to drop, maybe even to 100, just 100%, or maybe even below. And if it's a really huge transformer, 500, 600, 700 milliamp transformer, and you're only drawing 100 milliamps, it may be more than 110%. But that's a pretty good ballpark way to judge your power supply voltages, what kind of a DC voltage you're going to get from the from your power transformer. But you are going to actually have to measure this right here and not go by that, because if I just went by the schematic, I'd say, well, it's 115 and it's 700, so this is 350. Well, it's not 350, and I guess that's the real kicker right there. Okay, now let me show you what I've done here. I think you're going to like this. Okay, instead of using all of the greatest and fanciest and KT66s and 77s and 88s, I got to digging through a lot of my stuff here, and I came up with these two 6L6Gs. And not only that, but they are matched. Let's see, one of them reads 34 over 25. 25 is the minimum. The other one reads 35. So 36 and 35. I'd call that a matched pair. And not only is it a matched pair, but they're just absolutely beautiful. Look, the Sylvania faces forward on both of them. They're facing the pins. And I don't know if you can see it from the glare, but this says 6L6G, 6L6G. Even this is facing forward. And you know how picky we can be about that. They make all of the nicer tubes where all of the logo is on facing the pin. Now see, like here on these Sylvanias, they didn't do that. These are very, very nice Sylvanias, 6L6, 6S and 7, excuse me, the GTBs. They're just beautiful little tubes. But I thought I would do something with the vintage tubes, truly vintage. And of course, the mighty 5U4 back there. It's absolutely beautiful. The way that, look at the filament in that thing. Well, lights are all on. Let me turn mine on. Yeah, see the filament glowing in that 5U4 and the tops of those 6L6s. Let me turn out some more lights here. I know I'm bouncing around a lot, and my camera tends to make them a little bit more pink than they actually are. Let's set the camera back down so I don't make everybody dizzy. There we go. And not only that, but in my digging, I also found, this is amazing me, quite honestly, I also found some more 6L6s. These are 6, see, this one measures 39 over 25. Is that 39? Yeah. This one measures 36 over 25. Let the camera focus on it. These are 6L6 GAs. And not only that, but see the guide pin there? Even they face forward when I plug them in. I said, wow, now that, I just find that. And they work. They work great. 6L6 GAs and 6L6 Gs. And you know what? They perform absolutely as well as brand new KT66s or anything else. And these tubes are, I don't know, they could even be from the 40s. I'm going to guess the 50s, early 50s, if not 40s. I've been listening to my amplifiers a lot lately. Drives me crazy. But I noticed that something didn't quite sound right. I have some, the ones that I listen to out in the back house are called Dahlquist. They're called Dahlquist DQ20s. And last night I said, you know, I'm going to really look into these things. I bought these things used several years ago. And I remember when I bought them, there was a fuse blown in one of them, so I didn't think much about it. Just replaced the fuse, and I thought, well, that's fine. But in both of them, they both had exactly the same problem. If you look up the schematic to it, it's got some 4 ohm 5 watt resistors. 2 of them were burned completely open. So the crossover networks in there just weren't working at all. They sound so much better now that I've repaired them. So much better. I always thought they sounded a little bit gritty for some reason. I've kind of used that word recently in some of the my videos and some of the correspondence, you know, when we comment to one another. They don't sound gritty anymore. Anyway, let me hook this thing up so we can keep moving. I'll show you this thing performs. It's pretty amazing. Okay, I've got it set up. We're going to scan it. We're going to do the HP 8903, and we're going to scan it from 20 hertz to 20 kilohertz. Let's zoom out here and I'll show you quickly how it works. I've got it set up right now for 15 watts output, as you can see right here. That's a sine wave. It's at a kilohertz. You can see right over there. It uses this HP 8903 right up here, and it's hooked to the PC. It's run, the software is by Pete Millett. I don't want to go over all this kind of stuff right now. Here's a THD at the moment, 0.283. Now you'll actually see that over here too on the spectrum analyzer. Let's take a quick look at that. We'll just look at that briefly. I've got to hit run. That's what it looks like. You can see it wiggling there. Our 60 hertz is down minus 110 dB. I mean, they're down there. There's little spurs out here. There's our THD. There's our IMD. Okay. Now we go over to this one. Many of you have seen these run before, but I like to run them real time, so you know I'm really doing this. It says, is our reference level okay? I said yes, and I've got it set up to 15 watts, so I'll say okay. It starts out at 20 hertz. We'll see that start somewhere over here. Okay, it's starting at 0.7% THD. Drops very quickly. See, this is 20 hertz, 30 hertz. It's a little bit higher than the new tubes, but once it gets past the 20 hertz, look at there, it drops down to that's 0.2. And this is that transformer I'm talking about. It's the 40 Henry transformer. That's that Chicago BO-13. And at the high end, the 20 kilohertz stuff goes up a little bit higher than what we would like, ideally, up to 3%. Does it do a little bit better with the other tubes? Yes, it does. So without belaboring this and running lots and lots of stuff, I'll show you. Let me just bring this one up right here, for example. This is the same amplifier. I was tinkering with negative feedback right here, but actually it ends up just about 1.7% out at 20 kilohertz, and the 20 hertz down is down to about 0.4% THD with the new tubes. I think you can see that okay. I don't want to run these things over and over and over again. Let's see, what other ones we have. Well, that's one we just ran. There's one. There's some more. You can see that's with I believe the new Russian-made Genelex KT66s. THD is always down here at about the 0.4, and the THD is a little bit higher there. Yeah, up there it's 2-point-something%. But it just depends on how much negative feedback. See here, it's down a little lower. Here's down a little lower. See, this one right here seems to be. Well, that's when I did something. I don't remember how I got that one. That one was something really stupid. But anyway, you can see, I'm just really pleased with it. I've listened to it. I think it sounds marvelous. I'm very happy with it. Just some static test. Let's just run a couple of static tests on it, and I'll show you. We'll just take it out and we'll run it, single frequencies. So let's take it out of here and put it down here into the other oscillator, and I think you can see it jumped right back up to 15 watts where I pretty well had it at 2 kilohertz. If we go down to 20 hertz. Our 20 hertz at 15 watts, and it tells you the same numbers. Okay, well there's the display at 20 hertz. Nice and clean. Looks great. There's its frequency right there. There's its power right there. It didn't drop. And there's its THD right there, 0.8%. So it does indeed do low frequencies very well. The answers that we get over there on the scan are actually provided by the HP piece of equipment up here. It's just that the software running is displaying what that instrument is actually measuring. So there you go. Anyway, that was one of my goals. I wanted that transformer and I wanted to see what it would do. I think I've mentioned a number of times that a lot of my building is just simply to see and measure and document what these transformers actually do. And I have not been disappointed. The Acrosound, the James transformer, that's new stuff. They don't make them anymore, so they're going to become pretty hard to come by. And the Acrosound and this Chicago standard transformer all do an excellent job. They're all 20 watt or less amplifier transformers. Yeah, let me show you maximum power out of these old tubes. Let's turn it around here. We just got to look at a couple of things right here. We'll look at its power, and we'll look at well, let's see. Let's don't do it at 20 hertz. Let's do it at kilohertz where it's all that's standard. Let's see. We're going to go down to 10 hertz here. That's probably going to get pretty distorted. Now let's go up to a kilohertz. There we go. There's the kilohertz, 15 watts. That's 0.2% THD. If we run it up just to right at the clipping level, see it's clipping right. We can see that on the silk. That's 21 watts. That's 0.9. So it still does 21.2 watts at 0.983% THD. You can see that right there. So I call that 1%. So that's all the transformer is rated for, is 20 watts, and it actually does it. On once again on these beautiful old tubes. Boy, they just went all out back then. It seems like when they made this stuff. I haven't done this much testing with those 606 GAs, the little smaller tubes right here. But just the fact that I've had these for so many years and never really tinkered with them. See, 39 and 36 is how they measure, 25 being the minimum. I've also got some of these black plate, these black glass 6SN7s, and they actually perform really well too. They're World War II vintage stuff, so they're probably from the 40s. I'm guessing these might be too. Well, I hope you guys and ladies and gentlemen enjoy and stay safe out there, and carry on.